This
4 years.
recorded. All right. We're ready then?
Yep.
Okay. So my topic for this presentation is going to be understanding memory management. At first, I was going to do it about strictly about Rust. It was going to be called Modern Memory Allocation because everyone knows Rust is so modern, so incredible. But the more I wrote, the more I realized that it's actually not only about Rust that I'm not only going to be talking about Rust. There's some other lower level things which I think are generally good for people to know. So I changed title on Jacob again. He's going to have to, on his next LinkedIn post, generate a new image, right, to represent it. But anyway, here's the presentation. So let me start with a quick introduction. My name is Andre Fontenele. I'm 20 years old, and I graduated with my bachelor's in data science about a year ago. And since then, I've been doing quantitative development in the HFT space, working for a small startup. It's a great experience. I've been learning a lot. Most of what you'll be seeing today is stuff that I've learned in that year. And lastly, I'm not great at visual design. So yes, this is the basic default color scheme in Google Slides, and yeah, deal with it. Okay, so we're talking about memory management. If we're talking about anything, we should probably start with a definition. What is memory management? So the way I'm going to define memory management is that memory management is this task of figuring out where where in RAM our program's data is going to be stored. And there's a number of considerations which you have to take into account when you're figuring out where your data is going to be stored. You have the data, you need to store it somewhere. That's what memory management is. So you might be restricted by hardware limitations. Other running programs might be taking up space as well. And you might also just have general performance requirements. You don't want something to feel heavy, right? And you want to avoid taking up too much memory. You want to make your memory accesses fast. And memory management is this kind of like end-to-end process of all the way from the RAM chip. It collaborates with everything up the stack, all the abstractions up until your program, or maybe something slightly before your program. So with that as our definition, one thing that I'd like to stress very early on is that memory management is not an optional thing. So it's not something you can decide whether or not to do it, because it's happening, whether you realize it or not. Your program is generating and storing data, and that data is going to go somewhere. So the memory management is happening, you just don't know about it. And also, it's not something that we can easily ignore. Management is allocation and deallocation is some of the most expensive operations that we can do in our program, much more expensive than additions or subtractions or stuff, because you're moving data from much further away than you are in simple operations. So that's the purpose here. We're here to learn about approximately what this process looks like to get our program's memory onto RAM. And so before we really get deep into it, though, I'd like to do a little disclaimer here, and that is the scope that I outlined at the beginning. From our program to the RAM, we're not going to go over that because it's just way too much. We could reuse the old adage in programming here. In order to manually manage memory. Oh my goodness. You must first invent the universe. And we're not going to do all that. We're going to start quite a bit higher than actually, the error correction and the chips. We're not going through all that. Here are the 3 levels. We're going to go through 3 levels of memory management, and we're going to see how they build on each other, fixing each other's problems. So starting out, we're going to talk about CPU features and kernel APIs. And this is going to be our stack and our heap memory. These are our 2 options at that level. But stack and heap memory alone are kind of incomplete. So we have to build these layers on top of it to make it more useful. So the first level there is userland allocators. We have custom allocators, general purpose allocators, again, pros and cons. And then when we use those allocators, there's certain things that we can't do with them that will cause errors. So then we go to error prevention strategies. And then there are two kind of schools of thought there, automation and management. And we'll go through both of those. So let's start at the very beginning. A very good place to start. CPU features and kernel APIs are stack and heap memory. We'll start with the stack, and stack is something you're probably very familiar with, even if you don't know the name. Here we have a basic function in C, two functions. We have one is a sign approximation, right? And it's got variables, it's got loops, it's got inputs and outputs. And then in here, it calls, somewhere in the function, it calls factorial, this other function, which has its own set of variables, inputs, and outputs. So when we call this function in our computer, what it will do is it will navigate to the instructions here, which represent this block of code. And it will, at the same time, generate a little struct. And this struct roughly approximates the fields of the struct roughly approximate all the variables in the function. See, we have result right there, our inputs right here, our output, the return. And you can see we have everything that we need, all the space we need to do the operations on. And so we step through our functions instructions, and we fill out our fields until we get to here, when we need to call out to another function. And so when we call out to this other function, we do the same thing that we did for our sign approximation, and we generate another struct on top of that. So they're stacked. This is why we call it stack. We actually call it the call stack because it's the functions you call. And so this function will run. It'll go through its logic. It'll generate a return value. That return value will be copied in right here. And then we'll remove that from our stack. And so this is how the stack works. If you know scoping rules, you program in a language, like a real language, not Python, you're already intuitively familiar with this. This is just scoping rules. But you'd be surprised how deeply it integrates into computers. Stack operations, these acts of like stacking these structs on top of each other, they're very integrated with the CPU to the point where there are actually specific instructions just for pushing and popping. Let's name pushing and popping onto that stack. It doesn't take long, though, writing like this for you to figure out that there are some problems with the stack. And the two big ones is that allocations are not resizable and that they're tied to code shape. So if you tried to allocate something, let's say this result right here, and you wanted actually to make this an array, like we're gonna append two doubles after this. Well, you couldn't do that because the two places after it are terms and X, right? That's not, you can't overwrite that memory. And in the same way, it's also tied to code shape. If you tried to allocate something in factorial and then reference it in the sign approximation, you wouldn't be able to do that because the factorial is gone by then. And so because of these limitations, you don't end up using a ton of stack memory. So people tend to tie it to a very small capacity. On Linux, it's 8 megabytes by default. So
and you know what, Andre, can I stop you for a second and just ask a quick question?
Yeah.
You know, as I understand it, or could you describe the difference between how you're defining code scope and shape for me, please?
Well, what I mean by scope is that each function has its scope.
So the intent of the code, right?
Well, the scope is literally the brackets.
Okay.
So that's what I mean by scope. This is called a scope in C and in Rust and a good amount of languages. But everything in here, if I tried to allocate, say, like anything here, like F, and I wanted to refer back to it in sign approximation, I could not like just get an address to that point in memory, I couldn't just take a pointer of it, because by the time I'm down here to reach it, it's already been popped off the stack because the function's gone. Does that make sense?
Yeah, fantastic. Thank you.
Okay. So that's the stack. And then we
I got
have,
it. I got a quick question. So where actually does the stack live? Is this living on one of the registers or is this in RAM itself?
kind of both. I'm ignoring the registers on purpose. Uh, most of the times, like a good portion of these are going to be stored in registers. Uh, there's something called the ABI, the x86 64 Linux v ABI, and that kind of defines what a function is. You know, it'll say like the first what do you call it? First value goes in a register. The second argument goes in this register. The third argument goes in this register, so on and so on until you run out of registers, and then it'll say, and the rest of them you put on the stack. So actually, you kind of do prioritize the registers because they're faster, but I'm just simplifying here. In reality, you're right. A good portion of this is going to be happening through registers.
Right. Okay. So the uh the CPU prioritizes using registers first, but
Yes.
then the stack itself is in RAM.
Yes.
Okay.
And we'll actually see exactly where it is, but or I'll tell you. I didn't put it into the presentation, but yeah, that's true.
And Andre, correct me if I'm wrong, but it's not that the CPU, because this would be allocated at compile time, like which registers will be used.
Yeah, pretty much.
So yes, decided well before runtime.
Yeah, so all this is determined, well, not necessarily, because the exact order which things are stacked will be different, right? Because of branching. So just
Yeah,
because
I meant the register usage.
What?
I meant the register usage specifically. Sorry to.
No, don't be sorry. I'm glad to hear it. Although at this rate, we will probably run out of time. But no, I'm happy to answer questions.
Don't worry about running out of time. You just get through your presentation on your time.
Okay.
You're doing great.
Okay. Thank you. But yeah, is there anything else? But you're correct. These kind of structs and their layouts, the way it works is we have a stack pointer, which is stored in one of the registers, and it'll point to the beginning of this struct. And so the rest of the instructions will kind of base where they're storing stuff off of that offset and the registers. So it'll say like store it like X bytes away from the stack pointer, and that'll be power all the time, because we know that in this function, the stack pointer is always going to be set to the top of our function struct. Does that make sense?
Yes, makes perfect sense.
Okay.
Yeah.
Okay, good. Okay, so now we're going to talk about the other kind of memory. This is the much more flexible kind of memory. This is the heap. So the heap is given to us essentially like this huge array of bytes. We have this huge array of bytes. I believe it's something like 126 terabytes of heap memory. And it's split into these pages, these big blocks, they're called pages, of 4 kilobytes each. And by default, not all of these pages are actually writable. You can't write to this memory automatically when you start your program. And the reason for that is, we'll get to, but what you have to do if you want to use this memory is you have to request it from the kernel. So you'll issue a system call. On Linux, this is called memory map, mmap. You'll ask for a certain amount of pages, and you'll make that call, and the kernel will return to you an index. It won't be the page number. It will be the index of bytes that starts right up here, right? And it'll say you have 4 pages starting here, and it will unlock this or part of your array of memory, this part of your address space. And so now you can start writing in that memory. And then once you're done with it, you call a different syscall. And this one is memory unmap on Linux. And what it will do is you tell it where you started and how much you allocated. and it will deallocate that memory. And it seems like I must have removed the slide explaining why you need to do this. But essentially, the reason that you can't just use all your memory is because heap memory is kind of like a check to a bank. If you know anything about fractional reserve banking, you know that banks don't hold all the money for all the people who store their money at the bank, right? The way they are able to make money is by lending most of that out at an interest rate to people who need money, capital for something, loans. And so the CPU, the computer doesn't actually have 126 terabytes of memory. So we ask it for these amounts. And the truth is, not even all of this memory here, not all of these pages are necessarily going to be used for memory. This address space, this array, is an abstraction given to us by the kernel to allow us to interact with anything, memory being one of them. So this is how it's through this process of mapping these pages that you're able to actually interact with things, for example, that run over PCIe, like graphics cards. The kernel will map some memory onto this array. It'll tell you, hey, this memory corresponds to this GPU or whatever. And then you write into that memory, but you're not really writing it into the memory. The kernel, the kernel will convert those memory operations into messages that are sent to your devices. And you can do this also with disk. Does that make sense to everyone? I kind of went on a little there. Does that make sense how virtual memory is this abstraction given to us?
Yeah, that makes sense. So the kernel is also responsible for assigning read and write permissions too. Does it say, oh, anyone can write to this one, or so just people with these permissions? And it probably does the same things with reading as well.
Yeah, so is a permission system. I didn't discuss it in the slides here because it's out of scope. Frankly, most of what I just said is out of scope. But yeah, you're right. You can mark. We're actually about to get to that. You can mark some pages as like not readable or writable, or you can mark them as readable but not writable. And you can actually use this abstraction. If you map memory to disk or to a file, then what you can do is you can, from another process, map memory to the same place. And you can, by writing in one, see the data appear in the other. And this is very useful for making like ring buffers, which can communicate across processes. And it's not exactly a file you're writing to. It's like a file descriptor. I don't know too much about Linux, but it's like a file descriptor or something like that. But yes, you're right. Okay. So another operation that we're going to look at is memory mapping has this ability to reserve pages. And this is another very useful thing. We'll see why. So what reserving is if we ask, let's say, reserve 9 pages, it'll tell us start at page 3. And what this now means is that all these pages, now we know we can memory map them at request. So if I want to memory map, we call it commit at this stage. If I want to commit 2 pages, make them actually read and writable, I can actually now refer to some of my reserved pages, and I can say start at page 3, and it will open those 2 pages at page 3. And let's say I want 2 more. I can say start at page 5, and it will open to me 2 more. And so this way I can kind of control a contiguity here. We can see something resembling an array, right? A growable array here. And so this is the life cycle of a page, essentially, right? You can reserve it, and then commit it, and then release it once you're done. or you can just allocate straight to memory and then release. Yeah, and that's how the heap memory works. One other interesting to note is that the releasing of the memory will also happen if your program just shuts down. So you don't have to worry about your program shutting down and still taking up memory, right? That's managed for you. Okay, so that's everything about the heap. So if we think about the qualities of the heap, which makes it different from the stack, is that we have these large, like huge amount of memory, theoretically possible. You can use up as much of your physical RAM as you want. And the second thing is that these allocations are now kind of resizable using this idea of a block array, a page array. Or also resizable just if you want to like copy some piece of memory to another piece of memory and just a bigger piece of memory, right? And when I say not tied to code structure, I mean that now we access this through pointers and system calls, which we can call at any time. And we can keep those pointers for as long as we want. We don't need to worry about our function going out of scope and then it being deallocated by the stack. No, it's there. Okay, so that's the stack and the heap. If we think about these and the sort of ways that we can use them, there's one problem that is not solved by the kernel APIs that we need to solve in order to write programs. And that is that there's no kernel provided mechanism for flexibly allocating and deallocating large numbers of small objects. So in the stack, we have these, we can do these small variables, right? Like doubles, ints, these are like a couple bytes, but that's tied to code structure. That's tied to our scopes. On the heap, we're not tied to scopes, but we also just get like huge 4 kilobyte allocations. In order to allocate small things, we need to figure out how we're going to divide up this space that we have on the heap. And so that's where our second level of memory management comes in, userland allocators. And these are allocators that we or someone else writes in order to abstract these 4 kilobyte pages into actually usable sizes and figuring out how to split them up and when to allocate more and so on. For that, do we have any more questions on the heap and the stack? No? Okay. So userland allocators. There are a couple of things that we might want to do that we can't do with the kernel API. We might want to allocate small objects, right? That we already mentioned them. And we want them to have different sizes. And we want to be able to reuse some of that storage, right? Deallocate it individually. We want to control alignment, which I guess if you don't know what alignment is, don't worry about alignment. We're not really going to be discussing it. And then we want also to be able to allocate something on threads and share them across threads. Okay, so the simplest way that you could think to solve this problem is with a simple structure on the stack. So this is what we call the arena or the bump allocator. And so I have here like a basic idea of what an API for an arena might look like. We have a pointer to the start. We have pages, reserved pages, committed, and position. So pointer to the start is just a piece of memory that we map at this beginning, in this beginning call. We create a new arena, we map some memory, and we commit vastly more. We allocate memory, we commit it, and we reserve vastly more. So we might have like 4 pages committed, 4 pages of memory available to us. And then we can also reserve, you'd have to do the reservation first actually, but we can reserve like gigabytes of page space and then commit like 4 pages. And that will allow us with the system, we essentially just okay, we need 8 bytes of something. Okay, we have this position here. It's an array, and we just go 8 bytes forward. We look at where we were before, and we give you a pointer to that location when you allocate with an arena here, and we say, okay, there's your memory. And now we can use that memory until the memory is unmapped with the syscall. And you can also specify some alignment with that. Again, we're not going into alignment. I probably should remove that. And then, so you can allocate all this stuff. And then once you're all done with this memory, you don't want it anymore. You can destroy the arena. You can make the syscalls to what do you call it? Deallocate that memory. And it's returned back to the kernel, and you're done. So this is kind of the simplest way we might imagine doing things. But we can also make it a little bit more complicated, right? Because one of the limitations of the arena is that once you allocate something, like the amount of memory you're using only keeps growing. There's no way to reuse existing memory or to, like bump stuff off in an organized way. And so we can make some slight modifications and start adding that functionality in. So if we prefix each of these allocations in our arena with a little header, which describes the allocation and has a pointer to the next allocation and the previous allocation, we can create these linked lists of allocations. And then with those linked lists of allocations, if we have one that we're done with, we don't need that memory anymore, we can add it to a different linked list called our free list. And then next time we go to allocate, we can search through that free list of allocations we don't need anymore. And if we have memory that fits in one of those boxes, we can just say, okay, we're going to store our memory here. We're going to put it back into our stack and relink it up with all the others. Does that make sense to everyone? Linked lists, headers. Any questions?
Yeah, sorry. So these userland allocators that are primarily this arena allocator, this is also still managed by the kernel and still being managed by syscalls.
Well, you're using the syscalls. The syscalls are how you get the memory in the first place, and the allocators are how you manage the memory once you have it, and how you know when to request more pages and when to give up pages.
Okay, so when I'm writing my program in whatever language, I'm manually dealing with these syscalls, or is the kernel doing that for me?
So what a syscall is it's a function provided to you by the kernel. So when you make a syscall, you're filling out. We talked about the ABI earlier. You're filling out the ABI. You're putting all the stuff in the registers. And then you're sending an instruction which will perform an interrupt, and then the CPU will elevate its mode to the kernel, and then the kernel will take the data you have in memory and do an operation with it.
Okay, so all of this is being instructed at a machine code and assembly level. All these
Yeah, you can do this. There's also like C APIs, which allow you to do this. The memmap is C. You can call it in C. You can call it in assembly also, because assembly is like C translated. But and the reason we're calling it userland allocators is because all this logic right here, someone wrote that's running in your user space. It's not running in the kernel. This is running in your program. Or it's not. These are both custom allocators. They're very limited. I call them custom because they're limited like this. And typically when people use these, they write them themselves. And so this is how you manage those system calls, and you know when to call them in your program dynamically.
So this is the type of thing, if you were doing something super computationally expensive and very specific, you might create your own userland allocator to like manage your memory in a very specific way.
Yeah, like typically this will be if you'll have patterns with allocation patterns. For example, if your program only has one size of thing, you might just do an arena, because an arena with a free list, because every time you allocate, you're just allocating the same amount. And then if you free one of them and you add that to the free list, you don't have to worry about issues like memory fragmentation, which I was about to get to. So memory fragmentation is one of the problems with these kinds of allocators, especially with the arena, because you can't free individual things, reuse your memory. But if you're trying to reuse your memory, let's say you have this allocated, this free, this allocated, and you see, if you want to now allocate this size of object, well, it doesn't fit into any of these slots. You could theoretically coalesce these, but that's more logic, right? It doesn't fit directly into an individual free list slot, even though you actually have more memory than that. So that's one of the issues with these allocators, is when you use them, you have to be conscious of the sizes that you're allocating and deallocating. Does that answer your question, Jacob? Jacob?
It does answer my question. Thank you.
Okay, good. And so at this point, if you're not familiar with these allocators and you've written C before, you're probably wondering, where do malloc and free come into this? Because this is how most people who write C in low-level languages, and most languages kind of in general, interact with memory. It's through these two functions, malloc and free. Malloc, you call it, you give it an amount, and it gives you a pointer. And then free, you give it one of the pointers that you malloced, and it returns it. And you're probably wondering, where is this? This is actually these functions are a kind of userland allocator called a general purpose allocator. A general purpose allocator will sit somewhere in memory, and it'll be accessible by all your threads. And you make these calls to it, involving it, and you can allocate, manage things. So to give you an idea, we're going to go through a very popular, probably one of the most efficient, most practical general purpose allocators, and that's gmalloc. And this, we're not actually going to go through it. Actually, we're not, because this is what the gmalloc on the blog post where they introduced it, this is how they described it. This was their very helpful organization of the data structure. We have these threads, they're calling out to arenas. We know what arenas are, we've seen those. And then arenas have all these metadata things, and then they point to these red and black trees, which I don't even know. I'm not very good with trees myself, so I couldn't even tell you what those are supposed to do. And then they point, it's very complicated. You get the idea, right? And so there's a lot of logic that happens in general purpose allocators, which doesn't have to happen in custom allocators, because it's a lot more broad space. And strictly speaking, they're kind of more useful, right? They're more convenient. You'd rather just call a function to get memory than go through all this stuff of making system calls and then abstracting over them. You'd prefer to use these. And so that's how most languages work with these allocators. And so, yeah, I'm just kind of comparing the complexity here. So those are our kinds of allocators. Most people don't even know about the custom allocators. Like, they don't know that's possible. They're only familiar with malloc and free. And I think it's interesting because there's definitely some benefits if you know when to use them. So we've discussed our CPU features, our kernel APIs, how we get the memory in the first place. We've discussed how we divide it up, which is the job of the userland allocators. And now we have the problem of using those allocators, because there are mistakes that you can make with allocators, which are really bad. And we want to not make those mistakes. And so we implement these strategies to prevent those mistakes, those errors. So let's start. You might not know what I mean by this. Here are some basic kinds of errors that the three, I guess it's really two kinds of errors that you'll run into with memory. So let's see here. We have an array length and array data. These two variables together make an array. it's of a certain size. We get a size from the user, and then we allocate that amount of integers, and we get a pointer to that data. So we have on the stack, we have a size of our array and a pointer to the data of that array. And so we can do this, and we can do some stuff with that array. And we might even call a function, let's say sum, and we take the data and the length of the array, and we sum up all the integers in that array, and we put it on the stack. And let's say that was the last thing we needed. We don't really need the data of this array anymore. We just needed this sum, so we're going to free it. We're going to release it. We took it from our general purpose allocator, and we released it back to our general purpose allocator. And that's how these things work. Now, what would happen if we moved our free call from before our sum? Well, what would happen is it would throw an error at best. At worst, you might end up with corrupted data because you're telling the data structure, I want this memory, and then you're telling it, I don't want this memory. So your allocator will now feel free to use that memory for other things, to clear it out, to register other malloc calls from other programs, not other programs, other threads in your process. They might want to go there and use that memory, or that might have been the last bit of memory left in a certain page, and so now it deallocated that page back to the kernel. And so now when you go to whatever happens when you go to access this memory again, you don't get what you expected. There's nothing useful there. And so we call this a use after free. I don't know how they do it, but most general purpose allocators they'll panic here. They have a way to figure out that you did this as you do it. I don't know exactly how that works, to be honest, but it's one of the issues. We call this a use after free, and it's caused by this dangling pointer. It's a pointer which exists longer than the free and is used after the free. So this pointer is said to be dangling at this position after the free. One of the kinds of use after free errors is what we call a double free. And this is where you accidentally call free on the same data twice. And that causes problems because the second time when your allocator goes to look, pointer registered somewhere in its data structures, it's like, that's not there. What do you even want me to do? And so that will error as well. And then the last kind of error is a memory leak. So we have use after free, another kind of use after free, really, and then a memory leak. And a memory leak is when you just take the memory from the allocator and you never give it up. And this is not as bad as the previous two, because sometimes your program doesn't end up using that much memory. But if you're making an allocation like in a loop, that might be a problem. That might be a huge problem. So you don't want to take up unnecessary resources, and that's what memory leaks can do. So these are the two kinds of errors: use after free and memory leak. So how do we approach these? What are some ways we can solve through the first approach? The first approach is automation. So if you and this comes out in two different ways. You have garbage collecting and automatic reference counting. But the idea with automation is programming languages which use automation don't want you to know when the deallocations happen. They just want to do it for you. You're not supposed to figure out when to deallocate something. It will figure that out for you, and it'll just do it at the right time. So the first approach is called garbage collection. And I'm using two examples here, Go and Swift. The Apple languages, for some reason, are the only ones I've found which do automatic reference counting. Interesting thing. I guess it's just their thing, but it's an interesting technique we'll go over in a second. First of all, any questions about double freeze and memory leaks?
Yeah, I saw Tony wrote in the chat. He said, so it's like if I set out 100 t-shirts to wear for the month, but then a bunch of them got dirty for some reason, and I added them straight to the laundry pile.
I don't know exactly. I mean, is getting them dirty like returning them to the kernel? I mean, it's definitely a problem if you just buy all the shirts in town and then no one can get any shirts. That's kind of how I'd phrase a memory leak. Or a double free would be like if you go to get a refund and then you get the refund and then you go the next week to try and get a refund, there's going to be problems. So that if I had to make an analogy like that, I hope that solves the issue. I can't see the chat right now. I can only see my.
Yeah, he said the laundry pile equals avoiding talking to the kernel, or avoid talking to the kernel.
Well, yeah, absolutely. That's sure. Although you can absolutely dump. In some cases, we'll actually get to this later. We'll get to that later, because sometimes dumping all your t-shirts back in the laundry can be a problem, but sometimes it's not. And that actually, we'll see that in approach 2. So back to our so garbage collection, the way it works is essentially we have our program running, and then we have another program running at the same time. And the second program has read our source code. It, through some like black magic analysis, it has read our source code. It will look through our memory that we've allocated and figure out when no pointers exist to a certain piece of memory anymore, and free that piece of memory. So in this example, we have this function first word. We allocate a string here. Believe it or not, this is on the heap in Go, not the stack. Like a pointer to a certain part of it, and then we return the slice of that thing. And now, if this were the stack, when we called this would be invalid data, because we have our main struct on the stack, and then we have our first word struct. The first word struct is where on the stack we'd allocate that string, and then once we popped it out, it would be gone. So this would actually point to nothing if this string were on the stack, but it's on the heap, and so we can use it, and we print line, but then we never free it. It looks in a non-garbage collected language, and a language that doesn't use automation, and in other ones that don't as well. But anyway, in a language where you have to do the free calls yourself, this would be a memory leak, kind of. Not really, because the function closes, then that will automatically return the memory. But what Go will do is, let's suppose this one wasn't actually the end of the function, it keeps going. What Go will do is every once in a while, it will run the garbage collector, and it will look through all the strings that we've allocated, and it will look through all our variables and figure out which ones still have pointers. And normally, if you imagine trying to write that garbage collector, that program, it sounds like impossible. And it's really hard, I'm sure. I've never tried to, but I could never imagine how to write a garbage collector. But for some reason in Go, they make it somewhat fast, decently fast. And that garbage to worry about, what do you call it? Use after free, because the garbage collector will only deallocate that memory once no one's pointing to it anymore, once no one has access to it anymore. And then you don't have to worry about memory leaks, because the garbage collector will pick up all those unused data. Does that make sense? Any questions? Okay.
It all makes sense. I mean, it seems like in a very simple context, imagine you had a class and it's a private class, and it contains some functions and some variables.
Mm-hmm.
And when you declare that class or declare an instance of that class, your program is going to undoing its thing because it's a private class. It gets deallocated right away. It just gets really complicated when you have like public classes and things that are like referencing each other in like these complex maps.
That's true. And it gets easier with the second method. And this second method is something I think I'm actually going to look further into, using more of the languages which use this second method, because it's interesting. So the second method is called automatic reference counting. Again, only Apple languages, to my knowledge, do this as a feature of the language. But the idea is this: if you want to create a struct or a class, I guess, if the class has these things as X and Y, you can initialize it. But the idea is you can initialize this class, and the class will essentially evaluate to a struct with both fields, but also it'll have this hidden field called ref count. And this ref count is the number of, and this is specifically when you allocate to the heap, it's the number of pointers which point to that class. So let's say you allocate a class on the heap, the allocator or Swift will give you a pointer to that, and the ref count of that class will be 1. And let's say you then don't need that pointer. The pointer goes out of scope. Every time a pointer is deleted, either popped off the stack or removed from the heap, deallocated from the heap, before it goes, it will look at the thing it's pointing at, decrease the reference count by 1, and then if the reference count is 0, then it will deallocate that struct. And also, if you duplicate a pointer, you end up with 2 pointers to the thing. When that duplication increases the reference count by 1. So the reference count is quite literally the number of pointers pointing at the thing. And once that is 0, just like garbage collection, we can. And so this is typically, Swift is a pretty fast language. It's hard to compare how fast it is to garbage collection because, Go is faster than Swift in most cases, to my understanding, but also like Go is insanely fast in general. and Swift is much faster than most garbage collected languages. So it's hard to give an exact thing, but reference counting is just a very interesting approach. Does that make sense to everyone? Does anyone have questions about how automatic reference counting, not getting it, not understanding?
So it would also have the benefit then in real-time workloads over garbage collection that you don't have to stop threads, right?
Exactly. Yeah. You don't have to stop and look at the memory because it's just part of the process. And it's very consistent. The timing is very consistent like that. Yes, you're absolutely right. Some ChatGPT, you're absolutely right.
I know, every time I hear that in real life now, I'm like, oh.
Yeah.
Dude, it's same. Sometimes I say like, it's not this, it's that. And then I think, I'm turning into a LinkedIn bro. It's
turning into a sycophant.
Yeah, exactly. And I have to stop myself from doing it. But yeah. So that's automatic reference counting.
We had one question too,
which
was how do you keep the t-shirts from cloning themselves between the laundry pile and exploding in your closet?
I don't understand. Can you give an actual code explanation? How do you prevent?
I'll let Tony take that further if he wants.
Okay. Well, yeah. And
it sounded like he was worried about the same memory being allocated multiple times. Like a memory leak situation, maybe.
Well, you can't allocate the same memory multiple times if your allocator doesn't have a bug. That's a bug in the allocator. You ask for an amount from the allocator and it gives you the pointer. You never declare where the thing is. So that's not exactly like possible.
If I'm like creating a bunch of new instantiations of classes, and every time I create a new one, I forget to kill all the old ones, then we can have the t-shirt exploding in the closet situation. Yeah, I think he was just describing a memory leak.
Yeah. And also some of this I'm sure can be optimized away. like if your compiler knows that you're never going to take more than one reference from this thing, it can just not perform the check of how many is the reference count, right? So there's some optimization to be done there. And also there's one bug which is unique to automatic reference counting, which is kind of funny. So if you think about pointers as pillars holding up the memory, right? As soon as all the pillars are gone, the memory falls and it's deallocated. Well, if you have one class which is pointing to another class, and the second class is pointing back to the first class, both of their reference counts are 1. However, if you lose a reference count to either one, if you lose a reference to either one, then and you don't have any way to access them, they're just kind of stuck there in the ether of your program, pointing to each other, keeping each other alive. So sometimes in complicated like graph situations, I know that people do this thing where they have to manually decrease the ref count first. They have to free the pointer held by the thing so that the reference count of this is 0, and then it drops, and then as it drops, it follows that pointer, decreases the other reference count, and destroys the two. So they call that, I believe, a reference loop. And theoretically, you could imagine like a whole circle of these. But that's an interesting bug, which is unique to this kind of memory management.
But wouldn't the automatic reference counters already have logic to identify these reference loops and then account for that and just, I don't know, manually decrease it by 1?
Well, it'd have to be at runtime. The whole point of automatic reference counting over garbage collection is that you're literally just inserting code. So you take a reference and then you insert the code after increasing the reference count. So if you inserted like a complex check after each reference increase or decrease, that'd be like a ton of code that's running that you shouldn't need to run when you can just do it yourself, right? You shouldn't need to analyze the whole graph of computation every time you take a reference to something. Or that's at least the way I think of it. I don't know if that's the...
That sounds really slow. Yeah.
Yeah.
This is interpreted, right?
It sounds like if you have the skill issue, then you should just be writing in Python like me.
The garbage collection. True. Yeah. Well, we'll get to the skill issue solutions next. This is kind of like these are the ways I said automation. You're automating away all the things. You don't, except in the case of a reference loop with automatic reference counting, you shouldn't, with these methods, you shouldn't really have to think about memory. And so that's, yeah, that's helpful in some cases. So now we're going to look at the more hardcore approaches, and these are memory management. And so we have two methods, one which you don't see a lot of people talk about. It's kind of popular in some game dev circles, but not many others. And that's what I'm going to call lifetime coalescence. That's more of a practice than a system. But I think it's useful, and I think it has its place. And then the other one is ownership and lifetime semantics. And these are the things which, like, Rust is known for being hard. That's why Rust is known to be hard. It's because of ownership and lifetime semantics. Some other things as well, but mostly that. And C++, Rust actually got the ideas from C++ and kind of just redesigned them into a new language with some additions there. And Mojo is another language, although that's beta from my understanding, which uses this system. We're actually going to start with the ownership and lifetime semantics. So this is a lot of code. This is probably going to be a second before we understand this. But let's get an idea. So in Rust, we have this idea of an owned object, an object which owns its memory. And we have in Rust also constructors and destructors. Constructors are called manually. Generally, the convention is new, is how you do that. And then once they go out of scope, they're destructed. The memory is released. Okay, and you can escape it which is owned memory. Vector is an array. It's an array which you can reallocate, you can push onto it, you can pop off of it. It's a dynamic array. And if I return this from a function, it will keep living until it hits a scope close. Not with yeah, until it hits a scope close. So it exists here. We create it. We create a vector, literally a vector, and then we push some values onto it, right? And this, it doesn't get destroyed here because it approached the open brace as well as the closing brace. And then we do a random thing with it. We either push it into this function, and you'll notice in this function, once it goes into this function, it's not returned. So the drop call, the deallocation is right here at the end of that scope. Or we go down the other path, we do something with it, and it's destroyed in this function. Or if this function did nothing, then it would be destroyed at the end of this scope, because it was destroyed before this scope ends, so it can't exist past here. It's not guaranteed to exist past here necessarily. Does that make sense? Any questions? Okay. So, and this is kind of a nice visualization for that, right? We created it here. It travels through all these levels of the call stack, and it ends at some point, right? Either in the drop calls here. I guess it's actually, the vector is dropped here. This .iter thing turns it into an iterator, which turns it into a bunch. It's complicated iterators. I hate them. But yeah, it's dropped in this function. And so it is the space of program where it exists. And so we call this a lifetime in Rust. So if we remove the code and just kind of look at this one section, oh goodness, I forgot to make this more gradual. But the idea is that we have this lifetime. And so we know that for this lifetime of code, remember, this is the stack, right? We're entering a for loop, I guess not really another stack frame, but it is kind of like a new scope. And then we enter this thing, and this might go out to a function somewhere else. And so this red thing is the lifetime of our object. So the rules in Rust are that you're allowed to take a reference to the data in an owned object if you do so within this lifetime, and if that reference or the thing holding that reference is dropped before the closing of this thing above it. And this is determined at compile time. So people complain about Rust compile times being super long. Now you know why. Because Rust is, for every reference to every variable, checking all the possible places that the owned memory could go. That's the red. And then all the places the references go. And if there's any possibility that the reference makes it past a drop call, it'll raise an error. Say the reference exceeded the lifetime of the memory it was pointing to, right? You used it after its lifetime. And so we can take references at any point in this, and we can do several of them too, depending on the kind of reference. There's more rules in Rust, lots of rules in Rust. But that's the general idea. And so Rust will determine this statically. If we map this idea back to our, we'll see this is the path where our reference is. So we have our vector, we push things onto it, and then we create a slice. And a slice is kind of like a view into that vector. It's a kind of reference type. And so we create that, and then this is allowed to exist as long as the thing, the owned memory exists. And so you can see how I've kind of mapped that onto here. So any questions? This is probably the most complicated system. Because when you get to functions, like if you have to pass a reference, this function now has to statically check to make sure the reference exists for its whole lifetime, or the owned memory does. If the owned memory was moved out to another thread, for example, you can't guarantee that your reference is going to be valuable, is not going to point to deallocated memory, because the deallocation will be happening at a totally unknown time. But yeah, that's the That's the idea. Do we have any questions? Because yeah, I think I explained it rather well, but normally this takes like a couple weeks to get down.
So I don't really have a question, but let me just kind of repeat back to you
Mhm.
the kind of main idea. And so we have our main function here, and then inside of our main function, we are declaring a variable. Sorry, what is MUT? Sorry,
Mutable. That means
mutable.
it has like a functional flavor to it. Rust
Uh-huh.
does. You have to declare things as mutable. You have to say this is a mutable reference to a slice. Yeah.
Okay. So great. So you declare a variable,
Mhm.
and so that's called owned memory. That is owned by
This
main,
is
I
owned.
guess.
So the vector is owned.
The vector is owned.
And
Uh,
so,
and
yeah, continue.
and then at some point we have to unown that memory. And you said that a dot iter function is doing that later.
Yeah, so this is actually this is another function. If we want to, I could actually show you if we do a vector iter. This is a function. Okay, I'm not going to explain all that. Never mind. But essentially, iter is just a method which consumes that value and deallocates it as part of what it does. And it turns it into an iterator, which in Rust is something that you can use a for loop for on.
Sure. So I guess there's probably a couple different methods out there to
Yeah,
deallocate that
and you
memory.
can write your
And
own.
then
Uh,
and then the whole
this,
thing behind Rust is about tracking that owned memory and then making sure that references to that memory cannot exist outside of that
lifetime.
chronological ownership
Yes.
line.
And there's another thing too, which is that depending on, there's also different levels of references and certain rules about them to prevent other errors. But typically the way it works is for mutable references and slices, I'll say, is that from this point on to until the end of this lifetime, you can only reference this vector from the slice referring to it. You cannot like mutate the vector here. You can't like push another value into the vector after you've created this slice. And until that slice dies, you cannot operate on this variable. You have to use the slice. And part of the reason for that, if you imagine like writing this in C, if you're part of resizing in a vector might include reallocation. So if you run out of capacity and you need to push a thing to it, you're going to allocate a new piece of memory, copy your old memory in, and then add onto that new piece of memory. So if you have a pointer to that old memory, that's going to be freed at that point if you push and it decides to do this reallocation. So that's the reasoning behind stuff like that. Does that make sense?
Yes, it does.
Okay, good. Good. So that's probably the most complicated one. And then we're going to go over our last method, which is called lifetime coalescence. And this is more of a technique than a system. So all the things we've seen before, garbage collection in Go is built into the language. Automatic reference counting is built into Swift. Ownership and lifetime semantics are built into Rust, but lifetime coalescence doesn't do that. In fact, lifetime coalescence, you can do this, and it's more of a technique than a prevention method. Allow me to explain. So we've discussed lifetimes in Rust and how you can kind of assume that the value will exist. Well, this is Odin. Maybe I should have done C, but I like Odin. I'm starting to like Odin, and so we do lifetime coalescence with arenas. So if we allocate an arena and then we start pushing stuff onto it, then we know that that stuff will last for the lifetime of the arena. We can treat the arena like that owned thing in Rust. It's a collector of lifetimes. The lifetimes of all these things you're adding will as that arena does. So instead of managing several lifetimes for different values, you can just manage one in arena. And again, you do have to manually manage that arena. This little defer keyword works kind of like a destructor. It pushes this to the end, this free to the end of the scope. So you can create arenas, and then with these arenas, start pushing stuff onto it. And then as long as that arena exists, you don't need to check if I have 5 references to 5 different things in this arena, I don't have to check to see that they're all still valid when I look through my code. I can just see if the arena still exists. And so you're reducing the complexity of the problem drastically, because instead of making a call to a general purpose allocator, which exists for the lifetime of your whole program, you're making out calls to a allocator that's stored on the stack actually, and exists only for a certain point of time that you can see. And this is not as hard of a solution as the Rust ones, as the Rust solution or the automated solutions, but it can be very good if you're writing in a language which is unsafe, like C, where you have to manually manage memory. If you have to manually manage memory, this is probably the best way to do it. So what I'm saying. Does this method make sense? Because I know that this is the most subjective one, because it's not actually a hard guarantee. It's a technique that you apply in manually managed languages. Any questions about this or arguments? You think it's a bad method? No? Okay. So that's...
We've spent a lot of time talking about how these different memory management techniques work. And I kind of actually would like to learn a little bit about why we would use one system over the other. What are the performance implications? What are the safety implications?
Yeah.
What are the best use cases for one or the other?
Well, that's more, it's interesting because that's more contextual, right? It's more of a spectrum of performance, really. The worst performance is your garbage collection, because you... I heard that.
Same.
So we're back.
Yeah,
Okay.
we should be. I'm also recording on my device. Thank you.
All right. We're back, baby.
So yeah, Swift has that, but it's still a runtime solution. Rust is a compile time solution. And then Odin, or the arena method, is a programmer time solution. That's kind of the way you can look at it. And each of those has its downsides. If I had to say one thing for the lifetime coalescence solution or mitigation, it's that one of the qualities of an arena is that it's very cache friendly, because all your data is stored literally right next to each other. None of the decisions about where to map things are happening at runtime like they are in a general purpose allocator. And general purpose allocators are typically the kinds of allocators which are used in these other methods, like Rust, Go, and Swift. Rust actually uses gemalloc, the one that I referred to at the beginning. So they all have their ups and downs. Odin doesn't. The lifetime coalescence doesn't have the compile time problem that an ownership system will. An ownership system doesn't have the flexibility that garbage collection or automatic reference counting will. Automatic reference counting is better than garbage collection in many ways, although I've been assuming compiled languages this whole time. So one thing to note is that garbage collection might be more suitable for interpreted languages, because you're already running so much overhead, it might be better. It might be better. So that's something to think about for sure. I don't know too much about interpreted languages though. I work mostly in compiled stuff. I've touched JavaScript maybe twice, although I did get started in Python, and that's what I went to school with. But I'm not very familiar with those anymore. Yeah. So if I had to summarize like the pros and cons, that's just about it. There's some preference to it and stuff, and it also depends on what you need for your problem. There's an ease to the more automated solutions, which really is not there in Rust and lifetime coalescence systems. Yeah.
And in terms of safety and hardening systems against cyber attacks, I understand that there's a whole class of cyber attacks that seeks to access memory partitions that they're not supposed to have access to, or manipulate the heap in some sort of way. I've heard that for some reason Rust is better at protecting against these attacks, and I've no idea why that would be.
Yeah, so part of that is this ownership system, but there's some other stuff as well. One of the big ones, and this is one that Odin and most modern languages share as well, C does not have this, is a built-in idea of a slice or of a like a array. So in Rust, we have this built-in idea of a slice. We have them in Go, right? That's what this thing is. There's syntax built into it. There's none shown for Swift, but Swift has it. And when you have a built-in type like that, you can hard code into the type, and the compiler can insert checks to make sure that you're not indexing beyond the intended usage of your slice. And that's like one of the biggest ones. There's other issues because there's logic bugs, right? So you can still in Rust like make mistakes like that. But what you're not going to have is stuff lingering in memory longer than it should be. You're not going to have people accessing slices farther than they should, unless you use an unsafe keyword. That there's an intentional risk you can make in Rust where you can do more C-like operations, doing pointer math. That's probably the most simple way to put it, actually. Anytime you're doing pointer math manually is theoretically a chance for someone to take advantage of that, because it's not that math is not inherently tied to a check to make sure you're not going beyond bounds.
So if I was trying to execute an attack like that, I would try to locate a line where we're actually figuring out a number that will be put into the pointer, and I want to insert my special value into that so I can have it point at this specific thing that I want.
Yeah.
And
you can index past the end of an array into other memory. And I guess you could say that the lifetime coalescence system is more susceptible in that way because it's all stored and literally in a line. It's easier. But you can still have, and Odin does have, slice types, string types to mitigate that. And also another thing with C is that the way strings work is different. Most modern languages, strings come with a pointer and a length. However, in C, because of the time it was invented, strings just came with a pointer, and that points to a bunch of characters. And when you've reached the end of the string when you reach what's called the null terminator, which is literally just a 0 byte. And so it inherently involves like going and going in C, whereas in most languages, your length determines how long the string is, more like a traditional array. So that's
So
and
if you could like write over that null byte and put something else there, then you could get the C compiler to read something that it's not supposed to read.
yeah, and that's a mistake you can actually make. It's not too hard to make that mistake when you're trying to make your own strings, heap allocate them and stuff. It happens automatically for strings which are stored on the stack, but when you're storing on the heap, you have to manually insert that byte at the end. So that's a big thing. And at the time, I think it was supposed to make sense because you had less stack space than heap space. Like you were very limited on stack space, so you could only afford to store a pointer rather than a pointer into length. I think that's historically why it was done, from my understanding. Yeah. Anything else, or is everyone pretty satisfied? If we're satisfied, this is kind of the end of the talk. I know we have a new gopher in here. I think I don't know if he's watching at the moment, but there's some ways you can mix together these systems to get like unique flavors of memory management, and we can go over that if there are no more questions.
Yeah, I
Okay.
just like to hear about like specific popular languages. Like we work in Java at
Yeah.
my company. So what does Java do? I mean, it's garbage collected, right?
Yeah, so it's garbage collected and it's also interpreted, kind of. It's compiled into a byte code, which runs on the JVM, which is a binary. So that you have a program. When you're running a Java program, you're not running the Java program. You're running the Java binary, the JVM, which reads the file and does instructions, interprets your byte code, which was compiled from your source. So that's how Java works. And that's, I believe, also common across, I think Lua does that. Uh, I think Python does that, although there's like C Python stuff. Ruby definitely does that. Yeah, it's very common for a lot of these web languages. JavaScript, of course, is the big one.
The the way I understand it, the way I kind of look at it, it's called the Java virtual machine because it's basically a imaginary computer system that doesn't really exist, and then that it's like a specification for, and then the Java program is compiled to this fake computer, and then
Yeah.
this binary is an emulator for this fake computer, because then if you write the emulator for it, it'll run everywhere. That's the idea of Java, is write once, one, and run everywhere, or something like that was their like
Yeah,
slogan.
and that's a way better way than to explain it. Yeah, it's a compute you're simulating a computer on your computer. If it's a very simple computer that you're simulating, but you're simulating a computer. And that's also the idea with WebAssembly. WebAssembly is the same way. Although a lot of these interpreters they'll use something called JIT, or just-in-time compilation, where it will actually, like, instead of interpreting the instructions as they come in, it will actually take a bunch of Java bytecode or whatever and analyze it and translate it into a set of instructions and then run that set of instructions. So rather than taking each individual piece of bytecode at a time, it'll take these chunks and kind of like analyze them, lower it to machine language, and then run that. So that's another way that people do that. Although it's essentially just like batching, really. You're just batching instructions together. That's
Andre,
what.
I got a quick question. I'm sorry.
Yeah.
No, and I want to say thank you, by the way. Very detailed explanation. Oh, and great. But
Thank
I gotta like forgive me, this might be a little bit of a dumb question too. I'm just like, my expertise is not all the way there with this. When would you like, and I missed a little bit of the beginning, but when would you use this per se? Like if I'm programming something or I'm doing something in C or C, like I'm not thinking of this, right? While I'm doing that. Is it a specific like
Yeah, to kind of expand on what you're asking too, Mo, I think it's great because like imagine I prototype something with AI, right? But then I want to bring it into production and I realize like, wow, my cloud bill was, you know, super expensive, right? $100,000 this month, right? I'm using Python and I'm maybe over computing, right?
Mhm.
So in my head, the way I think about it is you want to go to these lower languages to be more efficient, right? And then you would spend the time and the money to maybe, rewrite some of your code base, or find efficiencies. Am I correct in that thinking?
That's one way. So both of these are good questions. So I'll deal with yours first, Michael. So one of the things that you can uh, use when you have this model is uh, approximately what your in Python's case, uh, Python, interpreted languages tend to be harder to manage your memory because it's obviously being managed by a very complex algorithm in your interpreter. However, there are some things that you can know about your interpreter which are still useful. For example, in a lot of interpreted languages, strings are immutable, meaning that every time you add something to a string, you're just allocating a new string. An allocation is a big cost. So you now know when you look through your code, if you're doing a bunch of these operations, you know that that's one thing you can look at. Figure out how you can do less of those operations. You'll have more efficient code. So that's one example there. For the other side, if you're writing in something low level like C, which doesn't have all the features that these different languages do, I'd say you can still take a lot from it. So one of the things is that reference counting, for example, which is what's used by Swift. And I explained how this works. It's actually something very common in a lot of C projects. They'll implement it manually. They'll have a ref count. They'll have a ref count variable in their struct, and they'll manually change it when they add pointers and stuff. So it's not as solid as Swift because it's not inserted by the compiler. But people still use reference counting as a very simple way to understand memory management around things like graphs. I know the Linux kernel uses reference counting. FFmpeg, I believe, uses it for some of their larger allocation stuff. But it's a very applicable concept. And in fact, people do this in Rust all the time when they have to deal with memory that's shared across threads, because automatic reference counting, as long as you're using operations which are thread safe on the reference count, you can actually share the memory and know that it will exist for that entire time. So you can still take these ideas, and again, this last one, lifetime coalescence, you can write your own arenas in C. The elites don't want you to know this, but you can write allocators yourself and use them. And a lot of people do. I think Quake and a lot of the earlier game dev stuff used pretty heavily these arena style custom allocator structures. So they're very popular in game dev circles. I don't know how popular they are in HFT stuff because I've only worked at one of these companies, but I know that that I find them very helpful for this kind of code. Even just performance benefit sometimes. If you're allocating only like two kinds of structures, boom, you just have two arenas and they're all there. You don't have to worry about moving stuff, having to reallocate your vectors. Is that sufficient, like, to satisfy you both?
Thank you. No, yeah, that was
Yeah,
actually, you touched right on that.
and just out
Shout
of
out to
curiosity, have you ever heard of Kokos? Kokkos?
No, is this a language or a?
It's as I understand it, it's what they use for like HPC computing to convert C++ to be more efficient on whatever hardware, right? So you write it once in C++,
No.
and then they use Kokos to convert that more to the specs of the actual machine, right? Because if you're dealing with
Yep.
100,000 nodes of parallel compute, you need to manage that somehow.
Yeah, that's
and be able to write, right? So just from a research side of things as well, a little unique perspective. I was thinking of, C++ is what's typically used for that as well.
Yeah, and that's an interesting one too, because there's plenty of ways you can do that. Like one of them is SIMD registers. There are certain registers in some CPUs which you can do one operation on multiple values at once. Aside from normal instruction parallelism, you can put your values into these registers and then add them all up, and they all get added to this thing. And that's whether or not those exist on certain machines is something you actually have to test. And I don't know about Cocos, but I'm assuming that's something that it does. And that's something you can also configure LLVM to do, which is funny mentioning LLVM. LLVM is, if you don't know, almost every big compiled language uses LLVM to optimize its code. Odin uses it, Rust uses it, Zig. I don't know if Go uses it. Mojo uses a modern version of LLVM called MLIR. C++, at least the Clang version, was one of the original languages implemented in LLVM. Swift was implemented in LLVM. Objective-C. Some of these were not. JS is V8. Interpreted languages tend not to be, but Go might have been. So it's it's such a complex problem, optimizing for specific hardware, that there's a whole thing built around that, and 50% of it is LLVM.
Two things, because one, I don't think you actually mentioned what LLVM is, so I'll just explain that. It's an intermittent representation compiler. So you compile code to LLVM code, and then LLVM actually optimizes it for the architecture. So what it lets you do is make a compiler for your program that produces garbage unoptimized code that is semantically correct and does what it's supposed to. But then LLVM handles the actual difficult part of making it into fast optimized code that runs across multiple pieces of hardware.
And yeah, exactly. And the reason people do that so much is because it's such a complex algorithmic problem. You have to do register. You have to figure out which values go in which registers to be most efficient. Which one goes in registers? Which one is going to go in the stack? And you have to figure out all this stuff. Actually, this value is only used to compute this thing, and this is a constant, so I can just put the constant there. And dead code, elimination, folding, loop unrolling. There's a lot of algorithmic complexity there, and people don't want to deal with it because they want their language to be up in less than 20 years.
Yeah, exactly. And the other thing, I'm thinking of it, on LLVM, they actually do real-time stuff too. I know RPCS3, the PlayStation 3 emulator, uses LLVM to do just-in-time compilation for its translation.
It can do JIT too, yeah.
Yeah, it's pretty cool. Anyway, sorry, random tangent on LLVM.
I love compilers. I want to write my own backend at some point, but again, it's going to take a while before I have the time to do that. I'm busy working, making money, and making presentations. Anything else? Or I thought I'd mention, if there are no more questions, one other thing, which is Go. Go, there is, for a period of time in Go, a push towards the lifetime coalescence model, where you were able to create arenas where the arenas were garbage collected, but the things inside of them were not. Meaning that you could write your garbage collected code, analyze where you could theoretically put arenas to make it faster, where you could do the manual allocation, and you could put arenas there and use arenas for that section of code. And unfortunately, it looks like they're dropping it, or they've delayed it. But that always struck me as a very interesting option, where you can have garbage collection by default, but you also can dip into like much faster manual allocation. So that's one of these interesting mixes that you can come up with. Yeah. It's funny. I meant to cover these, and then I get questions, and I get to explain manual reference.
No, you did a fantastic job. Thank you, Andre.
Okay. Yeah, and I guess I'll mention one more. This is one that's kind of like a pet project of mine, which is that Rust combining these two methods, lifetime coalescence and ownership and lifetime semantics. This is something I haven't seen anyone do, but I'm kind of interested in implementing. And it's taking this idea of an arena and giving it the same ownership semantics, the same compile time checks that Rust has. And so I've been working on a little standard library in Rust to do that. And it strikes me as like a pretty promising, it seems to me like it has potential. And so that's something I'm interested in that I've been thinking about in the past year. So if anyone's got any more questions, I think that'll conclude our time.
Yeah, Andre, I think I speak for everyone when I say that was very illuminating. Thank you so much for putting together this amazing, insightful presentation. Really appreciate it.
Yeah, I have to say, I think I might have learned more now than I have probably in the last, whatever, 4 years of college in 90 minutes, or at least it tied in whatever I had to learn, because at least I understood what you were saying, but maybe not low enough of a level to ask the questions quite like other people were able to. So, yeah, I thought that was fantastic.
Thank you very much. I appreciate that, because this is something that always struck me when I was learning to program, because I started college like 5 years ago, and I did data analysis, which for those of you who know,